You have a lot of homework this weekend. I will make your life a little easier this weekend. You don't have homework in this class. So, it's a one-time thing. Enjoy. You do still have the assignment, though. Sorry, I mean, that still exists. I'm going to go ahead and pass out the assignment now because there's some relevance to what we're actually going to be covering today. Well, there's a lot of relevance, but for particular reasons. So let me describe what we're doing. So you're going to be creating a Colab notebook. But here's a difference number one. You're going to be creating a notebook from scratch. So I'm not giving you a notebook. I'm giving you this piece of paper, which I will post as a PDF shortly after class. Okay, because it does have some links into it, and the links don't work as well from paper. So what you're going to be doing is what we started talking about on Monday, we're going to finish talking about today, which is using a pre-trained network in order to do our own categorization of images. Okay? But you're starting with this blank slate. There's really two challenges that you have. One, you're starting from a blank slate. Okay, so you have to create the notebook on your own. And two, you're limited in the resources that you can use in creating that notebook. In particular, you can't use any other notebooks. You can't use any tutorials. You can't use, for instance, the notebook that we go over in class on the video. You're limited to the documentation for Keras. Okay? Now the non-Keras stuff, yes, you can use tutorials. So for instance, you have to download a zip file or a compressed file containing the images that you're going to classify. And so if you don't know how to do that in Python, feel free to do a Google search and look it up and find out. I am giving you a template, kind of the order of things you want to do, but no idea of what parameters you're going to be using for that. You can look at the documentation. You can look at the source code to Keras if you want. Either of those is fine. Okay? Yes? You can't look at the past notebooks. No, you can't. Okay? So you're going to have to you'll remember, oh yeah, there was a fit, but what the heck are the parameters to fit? And where do I specify accuracy, and where do I specify the RMS prop, and all those things. And so it'll be a different form of frustration than the frustration you've had of choosing hyperparameters. This will be the frustration of figuring out what the parameters are. Okay? So I think it will be worthwhile. You shouldn't have to do a lot of hyperparameter choosing. And in fact, let me give you an additional piece of information for step 6. So for your optimizers, use default values for all your parameters is my recommendation. Okay, don't try and change things like learning rates. But for number 6, I left it kind of open as to put in some dense layers. I'm going to be specific, and I'm going to suggest something like did I do 1,000? Yeah, I think I did 1,000 I'll call it element, dense layer, followed by, I would throw in some dropout, right? Remember we learned about dropout on Monday. What does dropout provide? What's it good for, Susan?
To have some randomness in choosing which layers of things to include.
Which inputs to include, and why does the randomness good? It's a general form of
data.
It's not data augmentation because we're not actually augmenting the data, but it and data augmentation are both forms of regularization, right? So do a dropout with a 0.5, and then do your final dense layer. If we have 10 categories of images that we're categorizing, how big will our final layer be? So we have 10 kinds of images that we're classifying. One of them is like a tape cassette, and there are 9 others. So there are 10 of them. How big do we want our final layer? 10, yeah. So have a dense, and by dense, right, this is fully connected. So it'll be fully connected to whatever's coming from above, which we'll talk about. So a dense of 10. That's my recommendation. All right. So then you have less to play with, and it's more just working with code. And I'm sure I have the same problems everyone else has, in that if I am, well, let's just say copying and pasting code and making changes, I don't really learn it as much as if I am forced to look it up, look up the parameters, type it in by hand. That's what I want you to do. All right? And I do have a target this time. So I think it's 70%, which you should be able to do with little problem. I've actually gotten up to 85% validation accuracy. So a purely random would be what accuracy? That's right, if this were a binary problem, but it's not. What's our problem? 10. So the chance of being right is 1 out of 10. So that would be probably where your accuracy will be starting at, somewhere like that. Okay. Questions on this problem? And the data set we're using is, of course, not the big ImageNet data set, which has 1.2 million images. It's the cold version called ImageNet with a French accent, with a bad French accent, which I'm good at, which has, trying to remember the exact numbers of them. I think it's a couple thousand in just 10 different categories.
Can you talk about the choice between TensorFlow 1 and 2?
Yeah, what we have been doing prior to this is all TensorFlow 2, okay, and it has a little larger, what would you call that? Well, larger amount of boilerplate code you have to put in because it's not the default right now. Either one will be fine. The basic big difference that you'll sort of notice is that in TensorFlow 1, Keras was a separate deal, right? So Keras was a top-level module. So you would do import Keras, or possibly Keras dot layers or whatever you needed. In TensorFlow 2.0, Keras is part of TensorFlow. So it's basically TensorFlow dot Keras. That is the biggest thing you'll see. Some other small modifications are things like the names of some of the metrics. So you probably may have noticed MAE accuracy versus MAE, or val accuracy versus validation accuracy, or some other sorts of things you might have seen in this last exercise, where it's slightly different from how it's documented. And one person described to me how it changed from run to run, what that name was, which made their code hard to work with. So that was interesting. Other questions? So short answer is either one's fine. Josh. TensorFlow 2 is the new hot goodness, okay? It's fairly large changes. It just came out final within the last few months. And so going forward, it's probably what you want to be using. Some of the changes include things like there's an eager mode. So in TensorFlow 1, you created a computation graph in your code, and then you ran it. In TensorFlow 2, there is a mode the eager mode, you can just sort of be typing in Python, and it will be running and going. You don't have to have this one phase where you create a computation graph and then another phase where you run the computation graph. That's one of the biggest changes, and there's tons of small changes. Other questions? Okay. But the two biggies out there for neural network for deep learning frameworks are TensorFlow and anyone else know? PyTorch, yeah. I would say in academia, PyTorch is more popular. It is easier to make changes, test new things. TensorFlow is most commonly used sort of in production. So it's easy to take a TensorFlow model and deploy it, let's say on an Android or an iPhone or heavy duty in the cloud. So that's kind of the major differences between those. Okay. So we'll put this aside. If you have any questions, as always, do post them on the Piazza. Okay. And you might consider adjusting your preferences so that you do get email notifications as people post stuff. Because sometimes someone may post a question that whose answer will be useful to you, and you hadn't even realized that that was a question you had. So I would recommend that. If anything important happens, like changes to the instructions, I will go ahead and post that with whatever the setting is such that it gets forced to send email to you even if you haven't asked for that. But I try not to do too much of that. All right, this picture provides an alternate way to look at this network that you guys dealt with in your homework, all right? And it's different from how I've been presenting the convolutions and these various sizes in a particular way. I've been showing things as height, width, and depth. Okay. This picture kind of brings it 90 degrees this way, so that we have, let's see if I can do this right. Yeah. All right, so we have height and width here, and then the depth here, okay? The advantage of this is if then we apply a convolution that is of the same form, which looks like height, width, and depth. I'm getting better at this. Then it will produce something that is, let's say we have 15 of these. Then it'll produce something with a half padding. Then it'll produce something of the same height and width, but whose depth is now more, let's say. So its depth might be 10. It's like I'm having to do each of these from scratch. All right. So again, with our same height and width. So this height and width is supposed to be the same as that height and width. As we look through this picture of the VGG16, we're not actually showing the convolutions themselves. We're just showing the effects. Okay, so we see the input, which is some picture, and that is 224 by 224 by 3, right? This the RGB here. And that then turns into 224 by 224 by 64. So what causes us to go to 224 by 224 by 64? We do have our legend here, that's a convolution. 64 kernels, each of size. Can we tell from this?
3 times 3 times 3.
We actually can't tell from this that it's 3 times 3. We know the last dimension is 3, right? The depth is 3 because of this. But we don't actually know that it's a 3 by 3 unless we happen to remember that the VGG16 happened to use us 3 by 3s. So it's abstracting that out. We don't know that since this is 224 by 224 and this is 224 by 224 that it's half padding. And then there are 2 of these. So that means there's another convolution layer. Again, we end up at 224 by 224, so it must be half padding. We happen to know outside of this picture that it's 3 by 3.
Does half padding only refer to the 3 by 3, or if it's a 5 by 5?
If it's a 5 by 5, so we can either explicitly talk about the padding and number of pixels. So if we've got a 3 by 3, right, and we want to end up with the same size, we can use a padding of half of this thing, or we can use an absolute padding of 1. If we go to a 5 by 5, we can get the same effect with half padding, and 5 times a half is 2, right? Does that make sense? Okay. So, the kernels in the second layer, how many of them are there? 64, because our depth coming out of here is 64. We don't know whether they're 3 by 3 or not, although they happen to be. Now we drop down to 112 by 112 from a 224 by 224. We would guess that that would probably be a max pool. You could do it with convolutions with the appropriate choice of stride, but we have a max pooling. You see the picture here that shows the max pooling. The depth here. So what's the depth of coming out of the max pool? Can I give you choices? 64 and 128. So who's in the 64 camp? Okay, and who's the 128 camp? For coming out of the red here, the output of the output of the max pool. 64. All right, was everyone in the 64 camp, or was people in the 128? How many were in the 128 camp? I like it. Okay, 64. One way you can tell, it's only half as deep. If you look very carefully, I can see it because I'm really close up. But the other reason is because the max pool never does anything to the depth, right? Just takes the incoming depth, maintains the same incoming depth, shrinks the x and y dimensions. Now we do convolution. Again, half padding. We end up with a by 128, so that means I have 128 of them. 128 of them. 256, 256, 206 of them. 512, 512, 512 of them. Again, 512 of them. And we end up finally with our output of the final convolution layer, well, convolution slash max pool of, in this case, 7 by 7 by 512. Right.
Is there a general rule of how many parameters we should maintain for each layer? Or is it like that?
There's not a general rule. Commonly, one shrinks the size by half and increases the number of the depth by 2. So they kind of go sort of hand in hand, usually.
But we want to keep the number of parameters to be constant throughout the layers, right?
In general, we saw on Monday, right, which I guess was the homework, the increased from layer to layer, but we were balancing the number of weights. Let's think about that a second. So the number of weights actually continually increases, right? The size of the image doesn't affect the weights, does it? Right, if we have an image that's 1,000 by 1,000 or 10 by 10, as far as a 3 by 3 convolution is concerned, all it needs is that 3 by 3 by whatever its depth is, right? So in that sense, the weights are continually increasing if we are increasing the number of kernels, the number of features. But if we think about it like on the GPU, where we do have to actually hold the image or hold the output at any particular level, it's nice to be reducing that. So we're not using a huge amount of the GPU memory. Oh wait, so this is one way to fairly, oh sorry, we weren't quite done. 7 by 7 by 512. And then where do we feed that? Once we're done with convolutions and max pools, we feed it into a fully connected array. In this case, we feed it into a 4096. And notice now we're into fully connected. We're going to just talk about it as a 1 by 1. Okay. The fully connected layer doesn't think about it as a 1 by 1, right? It just thinks that it kind of is 4096. So we go from 7 by 7 by 512 to 4096, and then down to 1000, and then throw us off max it. So that's a reasonably good diagram of the VGG network. This is from the original paper. You'll see each paper describes their network in just different ways, pictorially. There's no common standard as to how things are shown. I'll just give you a quick example of another one, just to see what it looks like. This is from the AlexNet paper a year or two earlier. So it maintains this same idea of having the height and the width in this plane here, so that that is getting smaller and smaller, and it has the depth here. But it represents, for instance, max pooling just as this sort of shrinking here. Let's see, actually it's representing it's kind of a different way. It actually shows the convolutions. So this is 11 by 11 convolution that's running on this with a stride of 4. So if you have 11 by 11 convolution with a stride of 4, you're going to be shrinking the size of your image, which is exactly what this does, right? It goes from 224 to 55. And then they do a 5 by 5. And this is shrinking from 55 to 27. But there's a max pooling there that must be doing that. So they've got some non-uniformity, again, in how these things are shown. But it's important to be able to get an idea of what a diagram like this shows. Because these architectures keep coming out. And so you want to be able to understand it. And to my mind, a picture provides another look at what would otherwise be just a list of these are all the things we do, which I think is helpful. Any questions? So let us now return to this pre-trained network. So we have the VGG network. And in fact, let's go back to the picture of it. And here's what we're going to do. We're going to chop off what's called the top. Sometimes called the top, sometimes called the head. We're going to get rid of that. Then we're going to just be left with the convolution layers, convolution and max pools. So we're going to stop here. So we have our VGG network, and we have the parts of it, and we are going to keep the convolutional or base layers. So if we feed in a 224 by 224 by 3 image, we're going to end up with a 7 by 7 by 512. If we feed in a different size image, we're going to end up with a different size here, right? For instance, if we doubled this to 224 by 224 to 448 by 448, this would turn into a 14 by 14 by 512, right? In particular, what we're going to use is a 150 by 150. This is the sample that's used in the Cholette book for this. So we're going to have a 150 by 150 picture. And if we feed this in, we're going to get out any guesses on what size we might end up with coming out in the final, right? Which will be a someone said?
Yeah, around 4 or 5.
4 or 5, exactly. I think it turns out it's 4. 4 by 4 by?
Well, 5, 1, 2.
Yeah, by 5, 12. Okay? So every image we send in, we can get out this 4 by 4 by 5, 12. This is going to be approach number 1, and this goes over. This is repeating what we did on Monday. So approach 1 is let's call it feature extraction. Okay? We are going to basically take an image and extract the important features according to what VGT thinks. And we're going to do this for all of our, let's say, 2,000 images. So we're going to turn the ith image into a feature map. The ith feature map, right? Every input gets one of these outputs. Any questions on that? Is this fast or slow to do? And I'll help you here, right? These are pre-trained weights. Someone carefully trained us a VGG network on the 1.2 million ImageNet images. So we've got like 16 layers here. We've got to do 16 matrix multiplies with some max pools in there for each one of these. Not too expensive, especially if we're using a GPU and we can do stuff in parallel. So this is cheap, relatively cheap. We then no longer work with our images. Okay? We say forget our images, and we just work with these feature maps. So this is a carefully processed version of our image that has important features. Okay? These were features good enough to work with the ImageNet, all those categories. So distinguishing fire hydrants from dogs, I don't think there were pictures of both, from cats, from various kinds of birds, to school buses, to all sorts of things, 1,000 categories. Okay. What was in this network was those fully connected layers that told us, well, which of these features in which locations, in which combinations take you to which category. We don't have that anymore. Now, we create a new network. This new network is going to take a 4 by 4 by 512 input, and it's going to output whatever we desire. If we're doing a binary classification, it's going to output a single sigmoid. If we're doing 10 classes, like you're doing for your assignment, what do we want to output here? What's at the very end of this network? 1 by 1 by 10, yeah. We'll just show it as 10, let's say. With what activation function? Softmax. So I'll just show the softmax as a separate layer, even though it's really part of the last layer. Right? So how do we go from 4 by 4 by 512 to 10? We could have one fully connected layer that goes directly from here to here. But that probably doesn't provide us enough power, right? We probably want to say, what happens with some combinations of these things, and then what happens with some combinations of those things. So let's have at least one intermediate fully connected layer. So let's have a fully connected layer. In fact, let's use 1,000 like I had just said. Right? So this is a fully connected layer. Can we go directly from here to here? We may need to throw in a flattening here, right? In Keras, we would need to flatten it. So we could do fully connected layer here to 1,000. We could then throw in, let's say, a dropout layer here. And then fully connected. How many parameters do we have? About? How many parameters in the dropout layer? 0. How many parameters in the softmax layer? 0. How many in the connected layer from 1,000 to 10? Say again? 10,000. And from here to here? 512 by 16, so that's like 80. Let's get the right order of magnitude here, right? 16, that's 5,000 times 8,000 times 1,000 is 8 million. That's kind of a lot. Okay, 8 million plus a little bit more. How many of these do we have as inputs? 2,000, right? If I said we had 2,000 images, then we've got 2,000 of these feature maps. So we have 2,000 of these, 2,000 feature maps. And we run for some number of epochs. For every epoch, are we going through this? No, we didn't. We're done. We never come back to this. We go to here, and we say, okay, feed this in, backpropagate, fill in weights. Feed this in, backpropagate, fill in weights. These weights are all initialized to random values to begin with. Okay? So we do our forward propagation, backward propagation, forward propagation, back propagation, or forward pass, back propagation. And eventually we train this thing. We get some particular loss, we get some particular accuracy. Now we deploy it, right? We're out in the real world. Someone gives us an image, and we want to know which of these 10 categories is it. What do we have to do? We have to go back over here. We have to feed it through here, get our 4x4x512, and then take that and feed it into our second network. This is the fastest way to train, but the problem is we don't get to use data augmentation. Because with data augmentation, we don't really have 2,000 images, do we? We have every image is new every time, right? Sometimes it's rotated a little bit, sometimes it's zoomed in, and so on. And so the idea there are two ways we could do it. One way we could do it is somehow figure out what all our augmentation is going to be, feed in all those augmented values, store all those 4x4x512s, and then use them in all these epochs. But that's a lot of storage of these things you have to do. Why don't we just go ahead and smash these two together into one big network? And then we'll just run that one network for our training. Okay. So approach 1, feature extraction. 2 separate networks. For each epoch, run only network 2. Okay, to 2. Questions on this?
I have 2 questions. So if you were to smash the 2 networks together, then you would train a lot slower, correct? Because would you also be training?
Well, that is a good question. Do we like this? Do we like these weights? We like these weights. So therefore, approach number 2 is going to be lock these weights down, freeze them. Only weights we're going to be changing are those weights. Okay, so.
The second part is...
But then there's approach 3, which is, well, we like those weights, but couldn't we just tweak them a little bit? So, yes, second question.
And then, conceivably, would there be some way to, I guess, rather than data augment the image, you could do data augmentation on
this?
On Has there been any research into that or anything like that?
I don't know how you would do that. I mean, there might be some way to do it, but I don't know how you could operate in this different space and know what would be valid augmentation or not, right? The way we determine what's valid augmentation on the input is we say, well, these are the kinds of things we might see out in real life, right? These would also be reasonable images of dogs or cats or fire hydrants. So I don't know how you could do it. That's not to say it couldn't be done. I just don't know how, and I don't know of any research. Okay, so approach 2. We do have 2,000 images, that's true. We're not going to do this. We are going to have one big network. And I really like how I've drawn this because I can just go like that. Okay? So this is not a new network, this is a new head on the convolutional base. We take this base, we strip off this head, we throw on a new head. Okay. Among other things, the output size is different. This had 1,000 categories, we want 10. In another problem, we want 3 or 1. As you brought up, Ben, freeze these weights. That is, when backpropagation is happening, we just need to make sure none of these weights get updated. Okay. We are going to feed into this. So if we weren't planning on doing data augmentation, this is slower. Because every epoch, we've got to run through the whole network. And when we do backpropagation, the way it's implemented, it's not completely free not to update these. You've got to kind of run through each layer and say, oh, that's right, I'm not supposed to update this one. Oh, no, don't update this one. Oh, don't update this one. But it's mostly the forward propagation part, forward pass, that is expensive. But we are going to do data augmentation. So augment during each epoch. So we have our happy face here. In epoch 2, we might have a happy face that's rotated. Okay, that's really ugly, but it's a rotated happy face. And the unaugmented images, of course, will end up with exactly the same feature map as they did before. We'll continue on through, calculate the loss, figure out the gradient, feed it in, update these weights, update these weights, update these weights, update these weights, leave these guys alone, leave these guys alone, leave these guys alone. Do the next mini batch, the next mini batch, the next mini batch, and then through the next epoch, different augmentation, different values, great regularization. So we get regularization from our data augmentation. What other regularization do we have here? Dropout. What other regularization might we be using? Depending on, let's say, the optimizer.
Okay.
Yeah, weight decay. Does this make sense?
So the difference before was that we weren't augmenting the data, for example.
We were not augmenting the data. And the approach we took, we couldn't augment the data.
Why couldn't we augment the data?
The reason is we had taken the data and we had one time applied the convolutional layer and then saved these guys.
Okay, the code looks really similar, right, for these two. It seems to be
Fairly similar. The difference is we are actually going to create one model in the second case. And in the previous case, we actually have 2 models.
Okay, and whereas before we had like 2 separate for loops, now we have one big for loop.
Yep. Before we'd have 2 separate for loops. The first for loop would run through for the number of training images. And then the second for loop would run through for all the epochs.
And why would we do the first one and not the second one? It seems
Why the first one, not the second one?
Yeah.
If we have a fair amount of data that we don't need data augmentation, and we're going to run 100 epochs, to only have to run this whole thing once for all the images rather than 100 times, saves.
And then you don't augment before you train in because it takes too much space to store it. Is that correct?
It takes too much space to store it, and it's like extra work you're going through that you might as well just have one model that'll kind of take care of it on its own, right? Why write more code to end up doing the same thing? But practically, yeah, it'd be a lot of space. Okay. Although we did get some compression, right? We compressed our images from 150 by 150 by 3 down to 4 by 4 by 512, which is quite a bit of savings. But still, there'd be a lot of them if they were augmented.
So what do you mean by have a model that does the augmentation first?
Say that again?
What do you mean when you said have a model that does the augmentation first?
Have a model that does the augmentation first. I don't know. That's not ringing a bell, so let me think. I think I was answering the question, and see if this fits, that why don't we go ahead and do the data augmentation on this convolutional base and come up with all these? And then once we're done with that, go through and do all this training. And the answer would be you'd have to save all of these, right? You would have to both save all these, and you'd have to have more code because you have to run this one and then save it and then go and pull it back and run this one. Whereas it'd be less code to just have one model and run it all the way through. So we have these pre-trained weights, and these were ideal for ImageNet. We have now these trained weights, and these are ideal, or as close as we could get to ideal, for our problem. Is it possible that these weights could be tweaked to be even better for our problem? Yes. And so that's what we do as our third approach. So the third approach is approach 2 plus fine-tuning. So just see if there's something I wanted to say on this. Yeah, let's just put a summary of approach 2. So approach 2, every epoch use I don't really want to call it augmented data. I want to call it modified data. That's it. So we use modified data. The idea of using modified data is data augmentation. Right? So use modified data, forward pass through the big network. Right? So this is the convolutional base of VGG. Or we could use a different architecture if we wanted, as long as we had pre-trained weights. And then the back prop only updates our new head. Okay. You have a question there?
Can I clarify? When we use modified data, are we using the original data plus the modified data added to the data set? Or is it only the new model?
Yeah, so that's interesting. I'm not 100% thrilled with how Keras does it. So the way Keras does it, it's got a flow from directory, image data generator. And what it does is it will just make modify. It'll spit out modified according to what you've specified in terms of rotation and scaling and zooming and all that sort of stuff. I would prefer, and this is what is often done in PyTorch, although it doesn't come for free, is provide the original and one or a small number of modified versions of it. But so that you're always training for every epoch on the original data too. Okay. So you could have maybe, let's say, every time you do 5. The original plus 4 different ones each time. And so therefore, your epoch is running over, instead of the number of training images you have, 5 times the number of training images you have. Right? The original and 4 modifications.
Just as a clarification question, is the new head referring to like the end, like normal we're setting up?
This is the new head. Okay. So the base layers, or the base, and the new head. Right? And the old head was this one-dimensional part of it. All right, so the fine-tuning says, we've done pretty good now. Let's just see if we can tweak it to make it better. All right? So maybe we're getting some gradient coming back from here that we were just ignoring in here. But we want to be careful. We don't want to screw up a good thing. Okay? So we do not want to change all these weights. These weights at the very beginning of our network are some very low-level features that it's unlikely we really need to change. Towards the end here are things we might want to be changing as the features are getting higher and higher level. And we want a small learning rate because we don't want to change it too much. So the 2 things we're going to do in approach 3. First, we're going to completely finish approach 2. So we're going to completely train all this. And then we add on at the end fine-tuning. Okay? So now's the fine-tuning time. Let's look at fine-tuning. Fine-tuning time is going to say, so freeze these weights. Unfreeze these. The last few layers for some definition of few. Okay. So approach 3. I'm going to actually say here, finish approach 2, and then fine tune. And what's going to fine tune look like? Unfreeze. Last few layers of base. And then train some more with a low learning rate. So when we say train, we're going to forward pass through all the layers. And then back prop, updating weights. Which weights do we update? Just the last few here. Does everyone like that? But what if we make some changes here that might, on our next mini batch, affect here, right? Let me kind of give you an example. So let's say we had some features that are coming out of here that are not quite really what we were perfect, but we adjusted to them, right? We adjusted to use these semi-crappy features, or not perfect features. But now, if those features get perfect, we were working, just ignore it. So we were working, assuming we had these crappy features, and now they're good features, and so we probably want to adjust our weights. So we want to adjust not just these weights, but also these weights. So updating weights in head and unfrozen base layers. Right? So it kind of reminds me of the joke I heard of this guy who goes to see a tailor. All right? So he goes to the tailor makes him write a suit from scratch. You know, measures him, does all that stuff. He comes back to the tailor, he puts it on. He says, well, I mean, this sleeve is too long. This is not a problem. Actually, this one's too short. So he says, just kind of pull up your arm here, and then it'll look like this. It's the right length. Well, yeah, but also, you know, my pants here, this one is too short, that one's too long. Well, okay, if you could just kind of hold your foot like that, and then over on the shoulder, you know, it seems like it's binding here. Well, just kind of put your shoulder forward like that. Okay, so the guy leaves the tailor shop and starts kind of walking out like this, and someone else looks and he says, oh man, I need to use that tailor. If he can fit that guy, he can certainly do a good job for me. Okay? So that is kind of like having the crappy suit out of here, and this guy's getting used to it. Okay, but if you give him a good suit, he needs to adjust his weights for that. All right. Any questions on this? I did say on the assignments, so there was one out, I guess. So if you need to, when you're working on this, look at a notebook or look at the slides where we don't have a notebook today, but we had in the past. You just have to take a half an hour break before you go back to working on your assignment. You can't take notes. So.
When it says create the base model, does
Uh-huh.
that mean like you are importing a pre-built network from there?
And let me just show you what it looks like, what that code looks like. So, again. All right. So what you do is you call a VGG16 constructor and you say weights equals ImageNet. So that says, okay, I'm not going to use random weights. I will go ahead and download them from the internet and put them in here, and they're great weights. And then include top as false, saying, just give me the base, don't give me the rest. Does that explain that? And here you can tell it what size that you want. So in our case, it's 150 by 150. In your example, what you're going to be using, it's 160 by 160. So I think you maybe don't end up with a 4 by 4 here. You end up with maybe a 5 by 5. And right, the basic picture of what we're doing is this is the trained VGG16. We're ripping out the classifier on top of the convolution, throwing it around randomly initialized. And what is really useful is to do a summary. A summary gives you useful information when you've got a model. So it shows you, for instance, in this case, what your input is, given that we specified what the input is. That's optional. But if it knows what the input is, then it knows what all the sizes are going to be down below. Does it need to know the input size to know how many parameters are going to be? No, not for the convolution layers, because the convolution layers is independent of the input size. Right? And in fact, these numbers here, that's how I made sure that the last homework was correct. I took the model summary, made sure my numbers were the same as its numbers. So you can go through and see exactly what the sizes are going to be, what the number of weights are, and you can see that at the end, we end up as a 4x4. Trainable parameters is really important. So if we have this many total parameters and this many are trainable, how many of them are frozen? None. So we need to make sure to freeze. Right? You can freeze layer by layer, or you can freeze the entire model. I appeared to have an issue with freezing the entire model. And so if you're doing some layers that are trainable and some layers not, you're going to have to go through layer by layer and set them as trainable. I found I needed to do that anyway and just make them all be non-trainable. So set this up, make them all non-trainable, and then go make a new model from this.
Just to fully clarify this, when we set with like the original call you had for the VGG, and you had the
include top is false.
Including top is false. That's not that's just basically not giving us the head. What we're doing is that's just giving us the base. But we still think
The top is the head.
Okay.
Two different names for the same thing.
Okay, great.
Yeah.
I was curious, how does it work if you have a layer that trains and then you freeze it and then you train another layer? How does the back propagation work? I guess go through the first layer.
It's okay, right? If you think of it, the calculation of the gradient is still exactly the same. You're just not doing the theta equals theta minus whatever at that particular layer.
Is the gradient the more expensive part though, or is I feel like it's not saving a ton of. So it still seems pretty expensive if you still compute the gradient.
If you still compute the, okay, conceptually, well, so that's a good point. What it could do is find the last trainable layer and not compute any gradient beyond that, right? But it is also the case, though, if you had a random non-frozen layer in here, it'd still have to calculate intermediate gradients. It wouldn't have to calculate the gradient with respect to the weight, but it would have to calculate the gradient with respect to A and Z. I want to go over one more regularization technique. I think this is the end. I think this is the last regularization technique we're going to go over. So this regularization, so this is leaving convolutional neural networks and just general neural network stuff. And this is specific to doing this mini batch gradient descent, right, where we're doing batches smaller than the entire training data set. So let's say we have a layer K, and K plus 1. Sorry, let me give you a name for this. Batch normalization. And this is a form of regularization. And I will say, like much in neural network land, no one exactly knows why it works. Okay? But I'll give you some intuitions of how it's designed. And it works in practice. So let's look at what's coming out of this layer as we are training a mini batch. So let's say we have a mini batch with of size 5. Right? Batch size is 5. And this layer has size 3. What's coming out of this? What is the output of this? What is the shape of the output?
This is 1/3.
Okay, so 1/3 is a reasonable idea because, right, we go through and we do this, you know, z equals xw, well, aw plus b, a equals g of z, and we end up with this 1/3, except we're doing a mini batch. And so with the mini batch, what we actually end up with is a 5/3. Okay? Every instance of our input gets put into a matrix. Because usually our inputs are all 1 by whatever. Well, that's not quite true because for images it could be 224 by 224 by 3, let's say. But if we had 5 training instances, it'd be 5 by 224 by 224 by 3. We just add an extra dimension on to the input. And then that just kind of feeds through all of this. That we have an extra dimension, which is the training examples. So when we get to the end, we have, if it's a binary classification problem, 5 probabilities. And we feed that into the loss, and as we're coming back, we get these 5 gradients. Okay? And we're going to take the average of those as we apply it to each of the elements. So, let's say, coming out of this layer, we have, let's look at one particular column here. So we're going to look at one particular unit here in this layer. Right? It outputs a value, and for the 5 training examples, it outputs 5 different values for our mini batch. So let's say this outputs 1, 5, 10, 15, and 3. All right? So this is for batch 1. And for batch 2, we get some different values. We get -3, and 5, and 100, and 10, and -8. Right. And this, yep, go ahead.
Would they output 5 values or 3? Because I thought our batch size is 5.
Our batch size is 5. And so coming out of, there are 3 units in here. And we're looking at that unit. So this particular unit spits out 5 values. Okay? Now, I guess it must not be using a ReLU activation because we have negative outputs, right? So let's just stick with it. Let's say it's using some different activation function. So we can be getting these varying values because as we're taking the mini batch, we're taking a small sample of our total set of inputs. And so we can get some groups that are much different from other groups. They have very different characteristics. Their distributions are different, right? Their means are different. Their standard deviations are different. Not only different, very different. Right? If we look at the mean of batch 1, right, the mu batch 1, it equals 15, 25, 30, 34, so it equals like 7, right? And the standard deviation is, let's just say it's 3, okay? Here, so this is for batch 1. The mean for batch 2 is more like 21. And the standard deviation for batch 2 is more like 15. Okay? I am within an order of magnitude on both these standard deviations, I'll have you know. So the idea of batch normalization is that it can be hard for the next layer to be learning things if the means and standard deviations are just going wild and all over the place. That it's easier for it to learn if it has a more consistent mean and standard deviation. And so we are trying to normalize between batches the mean and standard deviation. That's the idea. Let me show you how that works. For each mini batch, B, calculate the mean of B and calculate sigma squared of B. Okay? So for this mini batch. Hey, there they are. Well, this is the standard deviation, so this is sigma, so sigma squared must be 9. Then adjust the outputs in the following way. And in fact, here's what I'm going to do. I am going to renumber this. I'm going to say this is k plus 2, and I'm going to squeeze in a batch norm layer k plus 1. Okay? So I'm going to say the output for layer k plus 1 is equal to the input for layer k plus 1. And I'm going to scale it so that we have 0 mean and unit standard deviation. Okay, so subtract what? The mean for this batch. Not any other batch, this batch. And divide by the square root of sigma squared. And just in case, as some of you had a problem with, I think, in the last assignment, just in case they're all the same value and we have 0 variance, let's just throw in some epsilon there so we don't divide by 0 because we don't like to do that. So now these guys are going to get converted to 1, 5, 10, 15, 3 are going to get converted to, and we're going to do some rough estimates here. So that's like a, well, this is easy. This is a 1 turns into a, if the mean is 7, how many standard deviations are we below 7? 2. So this is minus 2. 5 is half the standard deviation below, let's say, negative 0.5. 10 is exactly 1 standard deviation above. 15 is 8 is almost 3 standard deviations, so 2.5. And negative 1.1. Does that roughly make sense? And then for batch 2, so this is batch 1, batch 2, negative 3, 5, 100, 10, negative 8 goes to negative 1.2, negative 1.01, 100 is like 85, 5 standard deviations above. About those numbers, okay? I'm roughly guesstimating. But you can see here our range, right? This is what we end up with. And this range are roughly in the same range. And their mean is going to be 0. And their standard deviation is going to be 1. So we think k plus 2 layer is going to be happier because it's not going to have this wildly wobbling means and standard deviations. There is a problem, though. And that problem is, what if layer 2 kind of wants all these numbers to be bigger? Okay? How How is there an idea that comes down that says all these values should be bigger? Yeah.
Bias, just bigger bias coming out of that layer.
Well, we don't actually have a bias coming out of here. There is a previous bias we could be working with, that's true. But what I'm thinking of is if we look at sigma L, sigma AK, if that's negative, that says it should be bigger, right? And if this were negative for every one of those 5 training examples, then that would say these should all be bigger, which means it doesn't really want a mean of 0. But what would happen is we would increase these values, maybe just by the bias. Right? Maybe we just increase this bias by 10. But the next mini batch that comes along, we would carefully go through and renormalize to have a 0 mean, and we get screwed. Because the batch normalization is forcing the mean and standard deviation to be 0 and 1, even though that's not really what should be correct. Maybe there's some different distribution that we want, still to be the same from batch to batch to batch to batch, but not 0 and 1.
Just add 1 to all of them, so then it's now between.
We could add 1 if we wanted to have the mean of 1 instead of a mean of 0. But instead of adding 1, why don't we add a parameter, a variable that can be learned? So we'll basically say, hey, batch normalization layer, other layers like dropout and max pool didn't get to have parameters. We are going to give parameters to the batch norm layer. We're going to give two parameters for every input. Okay? We're going to give basically a mean, it's called a batch norm mean, and a batch norm standard deviation. Okay? This isn't one number. This is, in this case, 3 numbers, right? It's a vector of 3. But let's focus on one input and just vectorize. Imagine we're using NumPy and it's getting vectorized. So we take this, right? This is input k plus 1 minus the mean of the batch divided by epsilon plus sigma squared for the batch. This gives us a number, mean of 0, unit standard deviation. How do we change its mean? Add a number, right? So what we'll add is, let me just be consistent with what I normally use. Yeah. So we'll add a beta. Beta is used for different things. Every paper, they need a Greek variable, so they pick something, and they don't try and say, I need to be different from every other paper. So for batch norm, they use beta here. So beta will adjust the mean. And we adjust the standard deviation just by multiplying by so we have two different actually, I'm going to get rid of, so we're going to call this beta n. We're going to call this. These two are very different things. This is the mean of this mini batch. This is the mean that this batch normalization layer is learning. Okay? So we will be doing gradient descent with respect to this parameter. We will be doing gradient descent with respect to this parameter. We'll be upping it or lowering it as appropriate. And this layer will then be learning for this particular input what is a good mean and standard deviation to have. Does that make sense? There is a problem. And that is, this is great for training time, but at inference time, we know this, we learned it, right? We know this, we learned it. We have our input. But what about this mean for the mini batch? Do we want to be using, I mean, what if we just have one instance that we're trying to infer, right? One instance that we are doing test on. We don't want to be using the mean and standard deviation in the mini batch. We want to use kind of the overall mean and standard deviation of this output, right? And so therefore, as we're learning, we kind of keep track of what is this mean and standard deviation been and keep a moving average. That's we're out of time. I will review this on Monday. As always, I'll be in the cafe until 3:30. I encourage you to come by, even if you don't have any, if there's anything you're at all spotty on, just come by and we'll talk about it, okay? And if you ask nicely, I'll buy you a drink. Added bonus. Oh, and I don't think I said, did I say there was a quiz or not next week? No. So not only will we not have the homework, we won't have the quiz that the homework would have been practicing for. Okay?
It was comfortable, Aaron, that's not
Well, the thing for me is like, I was amazing at
Thank you very much.
And so I had a lot of fun. It was really, really amazing for a time. It was a party school. I was really good at that. Yeah, so like, never thought I'd ever be one of my parents. So I became my parents. And then it was really hard to get to it. Oh. I mean, all my classes were like 400 people. We could just like, huge auditorium.
So this is some state school?
Wisconsin, yeah. So you could sneak in, sneak out, not show up. Nobody would ever know.
I never had any class where attendance was taken. I took one like upper division math class where there were 8 people, and it's like, yeah, you had to show up or it was really embarrassing. But other than that,
Yeah,
no.
so I never spoke one-on-one to a single professor my entire life.
That
Bad, really bad.
it's so hard to convince people to go to office hours. I mean, that they're there for you and they're really handy.
You pay for it.
Yeah. Although some professors don't like it as much. Here, I think they all do, but in some cases,
My professors at CG were just like, it's boring, nobody ever shows up. Just
It's true.
sit there twiddling my thumbs. Till right before we have the exam.
so time is really ticking down for you, huh? Less than 2 months?
Yeah, so I'll find a job.
I'm going to be downstairs with you today because I got my first results from running my network on Rhodes.
Oh, yeah?
Yeah. I asked them to consulted, give their hand and the situation on the table.
Uh-huh.
And the baseline accuracy should be 84%. That's like how often you raise. I haven't.
Oh, so that's just like the average.
Yeah, that's the average. Like the 84% of the time you don't raise them.
Got it. Okay. So if you just say no, you get 84%.
Yeah.
Yeah.
84%.
Yeah.
And obviously the network hits 84% instantly, and it gets to about 93 point something, which is.
I think that's good. I mean, that is a good initial,
Yeah.
you know, better than random.
I'm wondering if it's perfect because it shouldn't be able to predict 100% accuracy because people aren't predicting. So if I look at the if I look at the accurate distribution, I haven't been able to do the math on exactly